how to calculate moment. So in this example, say let's say I'm holding a 10-pound kettlebell load at at 90 degree from my shoulder, and this is my shoulder joint. So it's making a 90-degree angle, and I'm trying to calculate the moment. As we explained before, moment is the what you feel in your shoulder because of this 10-pound load is the force and distance. Assume that the load is about 30 inches from my shoulder joint, which is the pivot point or fulcrum. So with respect to that shoulder joint or pivot or fulcrum, um, whatever you want to call, so that's going to be 10 pounds force times the distance 30 inches. So that's 300 pound inches. Now here, imagine a situation where this load is acting, let's say, at a 30-degree angle instead of this. So I'm holding the load, is same shoulder joint, so same distance. I'm holding now this time approximately, so that kettlebell 10 pounds, say for example, I'm holding at a 30-degree angle. As you realize that this is going to be way easier than this position. So if I'm holding the load at this position right here, it's going to be very, very easy. So the moment should reflect that as well. So moment is not really any distance. It is actually the distance between the line of action, the fulcrum or pivot, in this case shoulder joint, pivot point, and this distance. So the line of action of the force. So it's not just any distance. So moment is actually is the force times the distance between the line of action of the force and the pivot point. So not just any distance. So in this case, so if this 10-pound force now is not acting at 30 inches anymore, even though my hand length 30 inches still the same, but now it's acting way less away from my body. So it's much closer to my body. So this is the distance that is acting from the pivot point. So if we calculate this distance out of this triangle, we know this 30 inches. It's a 30-degree angle here. So this component would be 30 inches sine 30 degree. So that's the distance now, the line of action of that force. It's going to be 30 times sine 30 degree. So that is basically 150 pound inches. So it's not any distance, it's the shortest distance, perpendicular distance. Now, a lot of time it is easier to resolve forces when you work on moment instead of finding the shortest distance. And I will show you that technique here. So it's the same 10-pound load is acting downwards. Let's say at 30 degree. So instead of finding the shortest distance, what you can do is you can resolve this 10-pound force in a way so one of the component passes through the fulcrum, passes through that shoulder joint or pivot point or fulcrum. So then, we can resolve this 10-pound force in this direction, 10, this is a 30 degree. So 10 cosine 30 degree. So you can resolve this in this direction in a way that it passes through the fulcrum. The other component exactly perpendicular to that force. So then this would be then 10 sine 30 degree. Now, if you add the moment with respect to the pivot point, in this case shoulder joint, that's going to be the forces times distance. Now, I get this, the one passing through the fulcrum will not produce any moment because the distance is 0. It is passing through that same pivot point. So there will be no moment for that, no distance. Plus, we have this 10 sine 30 degree. So then this force times the distance 30 inches. So this is the perpendicular shortest distance, the length of my arm. So if you do all of this, it's going to be 150 pound inches. One more thing you have to know, moment has direction as well. And generally, if it creates a counterclockwise moment, in this particular scenario, this load will try to do this, my hand. So counterclockwise is assume positive. And then what my shoulder will do to counterbalance this, it will produce a clockwise moment of exact same 300 pound inches to keep me in this position. So clockwise, negative, counterclockwise, positive.